These sets of notes cover gravitation, specifically the law of gravitation proposed and currently accepted by Sir Isaac Newton. A little bit of the background leading up to the theory. Nicholas Copernicus, a Polish scientist, was the first person to propose that the Earth revolved around the Sun rather than the Earth being the center of the solar system. He was ridiculed for this, but eventually his model is now what we accept. Tycho Brahe took a great amount of data concerning the location of the planets. If you want to look up some weird stuff about this guy, he was kind of out there, as some scientists are. Kepler used all of this data that was taken by Brahe and developed three important laws of motion concerning the planets. We are not going to go through them here specifically, but they have to do with shapes of orbit and how quickly the planets move around the sun. Now, Halley's Comet, which I think many people are aware of, named after Edmund Halley, who discovered it. He kind of pressed Isaac Newton, he was a contemporary of him, to formulate a law of gravity to explain why Kepler's laws work. And what Newton came up with was a theory in which masses pull things towards each other. So if you look at this figure right here, here's a picture of the moon orbiting our Earth. And that there's an attractive force between the two, which actually pulls the moon inward and keeps it in its circular path around the Earth. So the gravitational force here basically is the force pulling to the center, hence the centripetal force, so that moon doesn't go flying off in a straight line into space. Right. Now, gravitation is attractive. It's always pulling masses towards each other. It is never repulsive. Now, the actual strength of gravity depends pretty much on two things. The mass of each object, as well as the center-to-center distance between them. Why I mention center-to-center distance, objects have some size to them. So when you measure the distance, you're actually going from the center of one object to the center of the other. So for instance, if it was between a person and the Earth, which is what your weight is, you would measure from the center of the person to the center of the Earth, which is quite a large distance. Right. Now, there is what's called a universal gravitational constant that's been experimentally found that allows you to get the actual value of gravitational force between any two objects. I'll usually refer to it as big G, so that you do not get it confused with little g. And the value of that found from experimentation is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. I know those units look very overwhelming, but those are just so that in the formula all the units work out and you get force units of newtons at the end. Notice it's in scientific notation, and 10 to the negative 11th implies that big G is actually quite a small number. Okay. So now the full formula is that the strength of gravitational force depends upon the product of the masses, so m1 times m2, divided by the distance squared between them, and then this universal gravitation constant, big G, is just a coefficient out front. Right. So a quick little sample problem here. Right. How much gravitational force exists between two people? We have to make some assumptions. The distance between them, we'll just say a meter apart, and assume that each person has a mass of 70 kilograms. If we use this law of gravitation here and plug everything in, both of our masses are 70 kilograms, right? Distance between is 1 meter. And lastly, here's that universal gravitation constant. And if you look at all the units, right, you get kilograms squared from m1 times m2, but they cancel out. You have meters squared divided by meters squared, those cancel, and we're just left with newtons. If we plug these numbers here, we get a really small value here of 3.3 times 10 to the negative 7 newtons. This force is very small, it's very close to zero. The reason for that is because the mass of each person is relatively small. Now, that changes when we talk about large masses. What our weight is, we called it the force due to gravity. That is specifically the force due to gravity between a person and the Earth. So now your one mass is quite large because the mass of the Earth is nowhere near 70 kilograms. Right. Another example between, say, a planet and the sun, right? The sun pulls planets inward. That's why they stay in either elliptical or circular orbits around the sun. Here, these are actual values for Mars and the sun, and a distance, a quite large distance between them. Right? If you were ever working with numbers this large, you have to be quite good on your calculator using scientific notation. Here, the solution would be done exactly the same way. Plug all your numbers in. Please remember to square the distance that is in the denominator. And now here we get quite a large force, 2.1 times 10 to the 21st newtons. So much larger than in the previous example. This law of gravity is sometimes referred to as an inverse square law. And if you notice in the formula, the distance is squared and it's in the denominator. So what this figure is trying to get across here is the further away you get, right, when you push objects away from each other, the force of gravity between them decreases and decreases by the square. So for instance, if you were to double the distance between two objects, the force of gravity between them would actually go down by a factor of 4. If you were to triple the distance between the two objects, the force of gravity would drop by a factor of 9. So that force tends to get very weak very quickly as distance between objects increases. Right. So this is a little thought question here, and I pretty much just went over it. If you take two similar objects and just push them apart so that their distance is now twice as much, the gravitational force between them would now be 4 times smaller than it was before. Okay. You will have plenty of practice working through some problems here utilizing Newton's law of gravitation.